Hello friends, welcome back to my channel, a physicist Buddhist in California. So continuing my series of lectures where I talk about famous books, or most of the time. Once I talked about my own work. Those of you who have been paying attention to my channel, I talked about my encyclopedia, which I've been working on since 2013. I'll talk about that in a future lecture. But continuing this series, in this lecture today, I would talk about a very famous physicist and his very well-known book. So his name was Sidney Coleman. So let me give you a little bit of a background, those of you who are not familiar with him. Sidney Coleman was one of the greatest quantum field theorists of 20th century. He was an American physicist and a professor at Harvard University. He passed away in 2013, and he's credited with having educated whole generations of quantum field theorists during his tenure as professor at Harvard University. So Sidney Coleman was an excellent lecturer. So that was one of his biggest strengths. He mastered quantum field theory and he understood it well enough to lecture about it in the language that most people could understand. So his lectures were very popular. Both students and even his colleagues used to attend those lectures. So later in his life, those lectures were compiled into a book, and that's the name of this book, Aspects of Symmetry. So this book is nothing but collection of Sidney Coleman's lectures on quantum field theory. So let me talk now a little bit about this book. So like I've already described, the genesis of this book, how this book came out to be. So what is this book about? So in this book, after giving a brief introduction of quantum field theory, what quantum field theory is, now then Sidney Coleman talks mostly about the symmetry and the symmetry breaking. So that's one of the deepest discoveries in physics of 20th century, the discovery that the laws of nature are governed by the symmetry principles. So what are the symmetry principles? Symmetry is basically, you could say, is extra structure built into a theory. So one example of symmetry, the very well-known example of symmetry is the Lorentz symmetry or relativistic invariance, where a particle moving at a speed close to the speed of light has a constant speed of a particle moving at the speed of close to speed of light has extra symmetry, and so that symmetry is given inside the theory. So if the theory is relativistic invariant, then that symmetry becomes part of the theory. So this idea can be extended to other symmetries. So this was realized after Second World War by physicists that, okay, so the nature can be described by these extra symmetries. And the first theory that came out was quantum electrodynamics, which has a U1 gaze invariance. So these symmetries, they are given the name gaze invariance. Gaze means it's an internal symmetry. It's not a symmetry as we understand. For example, translation symmetry is a symmetry. Rotation symmetry is a symmetry that a physical body remains invariant if it's rotated on its axis or it's translated on its axis. So for example, so this idea can be extended to internal space, and this is known as gaze invariance. So one very good example of that is the quantum electrodynamics, which has U1 gaze invariance. So this book that this series of lectures that Sidney Coleman gave, he talks in detail about these symmetries and how these symmetries determine the behavior of these theories. So basically, one thing that comes out is that symmetry determines the dynamics of the theory. So let me explain what that means. Take, for example, quantum electrodynamics has, like I said, U1, where U is a unitary matrix. So U1 means it's a 1 by 1 unitary matrix. So the photon carries this gaze invariance, and this gaze invariance, because it's unbroken, so this photon is a massless particle and it has infinite domain, which means the photon can free to travel throughout the universe. Okay, but on the other hand, there is another symmetry which is SU3 symmetry, where U again stands for unitary and 3 means it's 3 by 3, and S means the determinant of that matrix is unity. So quantum chromodynamics has this gaze invariance. Quantum chromodynamics is the theory of quarks and gluons, just as quantum electrodynamics is the theory of electrons and photons. Both carry the U1 gaze invariance. So in case of quantum chromodynamics, the quarks and the gluons carry SU3 symmetry. So this is what Sidney Coleman does in this book. He describes the basic nature of quantum field theory, the idea of gaze symmetries, and then he talks about what these gaze symmetries imply. Like I said earlier, symmetry implies dynamics, and one of the deepest secrets that physicists have discovered is that sometimes these symmetries can be spontaneously broken. So this is what happens, what's known as Higgs particle, or popularly known as God particle. So how that particle comes into being. So what happens is that there are two quantum field theories. One is electrodynamics, which has U1 gaze, and the other one is the theory of weak force. So this is a nuclear force. This is a force that leads to radioactivity, and that has SU2 gaze invariance. And it turns out that these two gaze invariances, U1 and SU2, can be combined above a some certain energy level. So if you go beyond, say, about 100 GeV, where G stands for giga electron volts, then these two gaze invariants can be combined, and you can obtain a single theory, which is known as electroweak theory. So this theory has a combined gaze group of SU2 times U1. Now, of course, we live in a lower energy world. So in the beginning, when the universe was created, it has extremely high energy. So these two forces, these two gaze invariances, were unified into one gaze group. And later, as the universe expanded and it cooled down, then this gaze invariance broke down, and so the SU2 and the U1 groups separated, and that's what led to the generation of Higgs particle, which in turn imparts masses to all the fermions. Fermions are the particles which spin one half. So this is where electron gets its spin. Its mass. So before the symmetry is broken, the electron is massless, but we find in our low energy universe that electron does have a mass. So this is where, by interaction with these Higgs boson, which come into being after this electroweak symmetry is broken, that electron gets its mass. So Sidney Coleman talks about this in great detail. He talks about the symmetry. He talks about spontaneous symmetry breaking. What are the of course he the mechanism behind the breaking of the symmetry. So he basically explains that in great detail, and then he talks about other theories, quantum field theory of quarks and gluons, like I said, quantum chromodynamics. And so all this is covered in his book in beautifully simple language. And of course, this is a book of quantum field theory, of course, so it has a lot of mathematics in it, but he explains that very well. And so this is the book that if somebody is interested in learning the quantum field theory from a master of the subject, then I would highly recommend this book. This is not a textbook, by the way, so he doesn't show you how to do actual calculations, like I've mentioned in my earlier lectures, that quantum field theory can be said it's Feynman diagrams. So in order to do any calculation in quantum field theory, one needs Feynman diagrams, be it quantum electrodynamics or electroweak theory or quantum chromodynamics. You just need to write down the Lagrangian set of the path integral, and then approximate that path integral using Feynman diagrams. So you need to understand what the Feynman diagrams are and how they relate to the structure of a particular theory, and how to evaluate those Feynman diagrams. Thankfully, none of that has to be done by hand. It's all automated. One uses computer programs to do it. But first step, one has to understand what everything means before one just cranks up the computer and does calculations. But anyway, so this book doesn't cover that. So if you want to actually learn how to do calculations in quantum field theory using Feynman diagrams, then you have to use the textbooks. which I have reviewed in my earlier lectures, like the famous Introduction to Quantum Field Theory by Peskin and Schroeder. And there is another quantum field theory book by Matthew Schwartz, which is also an excellent source if one wants to learn how to use what Feynman diagrams are, and what role they play in doing calculations in quantum field theory. Okay, so I think this, and of course, there are areas in quantum field. So actually, by the way, so to finish my lecture, Feynman diagrams are very useful for, so here one has to make a distinction. Quantum field theory calculations can be done in two different ways. One is perturbative and one is non-perturbative. The perturbative part, which means that you have a small parameter and you can do a series expansion. So if the parameter is smaller than 1, then you know from basic mathematics, let's say, for example, the value of your parameter is 0.8. So if you square it, you get 0.64. If you cube it, you get an even smaller number. So as long as the parameter size is less than 1, you can make a power series out of it, because you know each subsequent term is going to be the smaller one, smaller than the one before. And this is known as perturbative expansion, and the quantum field theory calculation done using this method, using the Feynman diagram, is called perturbative calculation in quantum field theory. But it turns out in some cases this method fails. For example, let's take the example of quantum chromodynamics. Now, quantum chromodynamics is the theory of quarks and gluons. Now, a proton, for example, this is a very good example, has 3 quarks in it, 2 up quarks and 1 down quark. And these quarks are held together. They are interacting with each other through particles known as gluons. So gluons basically play the same role in quantum chromodynamics as a photon plays in quantum electrodynamics. So 2 electrons interact by exchanging photons. So that's what quantum electrodynamics is about. So similarly, in quantum chromodynamics, 2 quarks interact with each other by exchanging quarks. But it turns out that at low energy, where the quark we find a proton in the nature, the force is too strong. So that's why it's called, by the way, the quantum chromodynamics is the theory of strong nuclear force, just as quantum electrodynamics is the theory of electromagnetic force. So classical electromagnetism is described in quantum field theory by this theory called quantum electrodynamics, which actually describes what electromagnetism is, where does it come from. So quantum chromodynamics describes the strong nuclear force, and it turns out this, unlike quantum electrodynamics, this force behaves in a very different way. It actually becomes stronger at longer distances. Yes, now this is very counterintuitive. Everybody knows that if you have 2 charges and if you bring them together, they interact strongly, and as you take them away, the interaction weakens. So the interaction between the 2 charges, the electromagnetic interaction between the 2 charges is inversely proportional to the distance. As the distance increases, the interaction decreases. But in case of quarks, it's the other way around. As you take 2 quarks, suppose they are here and you have some interaction. As you pull them away, the interaction actually increases. So what happens at low energy, where we have a proton, this interaction is so strong that you cannot handle it using a perturbative quantum field theory. So because the perturbation, like I said, the perturbation expansion depends on the fact that you have a small parameter, but here you don't have a small parameter. So here one has to use what's known as non-perturbative methods to do a calculation in quantum field theory. So these non-perturbative methods, there are many of them, and one of the most popular one is known as 1 over n, where n is basically is just some number which is huge. So you don't have a small parameter. So what you can do, you can turn the problem around. You can take a very large parameter and you can take the inverse of that. So you make n to be very large, and so then you have 1 over n, which is a very small parameter. So for example, how you do that? For example, you can think of a completely hypothetical quantum field theory with SUN gaze. Now, here U is unitary, N means it's an N by N unitary matrix, and S means the determinant of this matrix is unity. So we can let N go to infinity. So it's a humongously large unitary matrix, which is infinitely large. It has infinite number of rows and infinite number of columns. So now what happens, because N is so large, then 1 over N would become a small number, like it's elementary mathematics. If you have some number which is infinite, then 1 over infinity is 0. So this is one method, which is very popular method to do non-perturbative calculations in quantum field theory. So this method is very useful in quantum chromodynamics, for example. So uh, Coleman talks about that in the last chapter of his book. So he covers, so once again to recap, he talks about quantum field theory. He talks the central role played by the symmetry, and in the quantum field theory, he talks about renormalization and renormalization group. He talks about symmetry breaking, and of course, quantum field, renormalizable quantum field theory with broken symmetry, which is what leads to Higgs phenomenon. And he talks about, of course, which is also which is renormalizable anyway. So then he talks about quantum field theories which are in principle renormalizable, but only non-perturbatively. For example, quantum chromodynamics at low energy. And he talks about the mathematical methods that people have developed over the years to handle such situations. One very powerful, very popular method among theoretical physicists is 1 over N method, and he talks about that. So with that, I come to the end of my lecture. I hope you found it interesting and knowledgeable, and I hope to see you again in my future lecture. Thank you.